Hey everyone, operating cloud services at scale reliably is challenging. Today, I'm going to talk about some of the research we are doing at Microsoft on addressing this problem using generative AI. I'm Chetan Bansal. I'm a researcher and research manager at Microsoft working on in the space of AIOps. At Microsoft, I'm part of M365 research group where our mission is to drive advancements in AI and systems to help Microsoft build best-in-class productivity experiences. In this group, we work on AIOps research where we leverage AI and data-driven techniques for driving step function improvement in cloud efficiency, cloud reliability, and developer productivity. In AIOps research, we have three main target stakeholders. First, we want to leverage our research to drive cloud and data center efficiency and reliability. Second, we want to improve the experience for our customers by automating support. And lastly, with tens of thousands of engineers at Microsoft, we want to improve their productivity and build best-in-class developer tools. In this space, our North Star is to holistically improve the reliability of our cloud services and infrastructure using context-aware and reliable intelligent assistants. So when we talk about software lifecycle, why is it challenging to build reliable cloud services? The first big non-obvious aspect here is that software lifecycle is actually much broader than writing code. It starts when we are designing features, when we are writing specs, then we start writing code, we test the code, we deploy the code, and then once the code is deployed, we have alerts and incidents caused by anomalous behavior of these services, and which requires us to understand these alerts, triage the alerts, and then diagnose and root cause them. As you can imagine, most of these steps in the software lifecycle are human-driven, which makes it to be error-prone. There's a lot of tribal knowledge which gets accumulated, and engineers have to do a lot of repetitive, non-standardized workflows, which requires a lot of human effort and toil. We conducted a large-scale study of production incidents at Microsoft a couple of years back, and what we learned was that this space is really complex, and for on-call engineers, for our SREs, they have to really understand the domain knowledge, leverage various tools, and handle different type of production incidents. For example, if you look at the chart here, incidents can be caused by a variety of root causes. They can be because of code bugs, dependency failures, database configuration, deployment, and even authorization failures. Similarly, the solutions to these failures are also complex and vast. For example, a lot of these incidents are addressed by rollbacks, infrastructure change, and sometimes even external fixes. So our takeaway from this study was that the majority of production incidents are surprisingly caused by non-code and config issues. And reducing human intervention in this entire software lifecycle and reliability incident lifecycle can result in significantly less incident impact. So our moonshot here from our team is to develop state-of-the-art tools and techniques that can not just understand developers' intent and their context, but also learn from the rich data and signals which are emitted continuously throughout the software lifecycle. For example, even when you're writing code and you're doing code reviews, there are pull requests, there are build errors, there are several other signals which are emitted. And even in the software life, once the software is deployed, you have metrics being emitted continuously, logs being emitted. So how can we take this entire rich knowledge and then use that to automate complex and recurring incidents, workflows, and proactively assist the engineers throughout this life cycle for decision making? With that in mind, we started working on using generative AI for improving cloud reliability. So far, generative AI has been shown to be really helpful for developers in writing code, which we have seen with GitHub Copilot. So we started leveraging foundational LLMs and pretty quickly figured out that they lack the domain adaptation, the tribal knowledge, which is required for providing actionable and relevant feed recommendations for root causing of incidents in production. So we leverage in-context learning to adapt the LLMs to the space, and we have deployed this work across Microsoft. But again, that has various limitations, which I'm going to talk about. So then we try to build better and more accurate solutions using agentic approaches, where we can also not just leverage the historical knowledge, but also leverage the tools and artifacts which on-call engineers actually use when they look at incidents. And throughout this journey of conducting research, building tools and techniques, we also learned inherent limitations in terms of lack of standardization or even a principled approach to designing AIOps tools. So we worked on AIOpsLab. We designed this framework which can help practitioners, engineers, and researchers on developing the next generation of AIOps tools. To start with, we leveraged in-context learning at Microsoft, where we built a corpus of over 100,000 incidents, from historical corpus, and then leverage in-context learning to domain adapt the LLMs using this pre-processed data sets. With that, we were able to deploy the solution across Microsoft to over 100 teams. And we got quite good feedback from the engineers in terms of helpfulness, usefulness, and accuracy. The current, based on user evaluation, the recommendations have over 50% accuracy. Majority of the engineers do want to continue using the recommendations, but as you can imagine, we don't want to stop here. While 50% accuracy is great for this complex task of reasoning over the software's lifecycle and anomalies, we quickly realized that there are also various limitations in this approach. So far, we were basically leveraging the historical knowledge corpus and trying to do reasoning and recommendations. But we figured out that engineers also do plethora of other things. For example, they might leverage troubleshooting guides, they might run some data queries, they might look at the logs, and ultimately they follow this complex process to root cause and diagnose incidents. So why can't we mimic that using generative AI? And that's exactly what we have done. So we leverage agentic approaches and chain of thought reasoning along with the additional tools and which are used by developers to do automated root cause reasoning for cloud service incidents. Why AI agents? Because AI agents can build on top of the natural language capabilities of large language models and then be able to interactively complete and complex workflows. They're able to leverage the knowledge from different knowledge sources. They can integrate with the various tools which developers already use, and they can also keep human in the loop for complex task completion. In order to do that in the AI space for cloud reliability, we are building a unified knowledge space where we have the risk data from the historical incidents, the postmortems, the root causes, the service metadata, the monitoring infrastructure, and so on. We also integrating the AI agent with the existing tools which are used by the developers. And lastly, we want these AI agents to continuously improve over time from the feedback and mistakes in prior executions. So we have this active learning loop for these AI agents. With these insights and back context, we have designed Flash, which is an agent for automating incident diagnosis. As we were designing Flash, we learned that LLMs are prone to hallucination and they can have a huge challenge in terms of automating or following complex instructions and workflows. So in Flash, we have built status supervision where we break down complex workflows into granular steps. And also, we are able to identify the expected outcome of these steps. And secondly, AI will never be 100% accurate for such complex tasks. So how can we learn from our mistakes? How can the AI agent learn from the historical mistakes and then avoid making such mistakes again and again? For that, we built hindsight integration. Here you can see the entire architecture. If you start from the top left, like we build a sort of hindsight corpus, which is a online active memory, which keeps getting updated as there are more and more, as there are mistakes and human feedback. We have the instant diagnosis toolkits, which are used by engineers, so which can be invoked by the Flash agent. And ultimately, it leverages large language models like GPT-4 for the reasoning capability and the natural language understanding capability. The other thing we learned, the other insight we had was developer tools need to be easy to be tested and have reproducible behavior. So we have also built auto evaluation layer, which can be used to evaluate and test Flash itself over and over again. In terms of evaluation, we have done extensive evaluation of Flash at Microsoft on production incidents. And the key insight here was that to do continuous and iterative and repetitive evaluation, because as I said, LLMs tend to hallucinate. So unless these tools and agents can have consistent and reproducible behavior, they cannot be trusted by developers, especially in a production scenario where they are dealing with a production incident. And here you can see that we did a continuous evaluation of Flash over production incidents, and we compared against various state-of-the-art frameworks and techniques like React. Lastly, I'm going to talk about AIOpsLab, which is our effort for building a principled and standardized approach which can be leveraged by practitioners and engineers for developing more agents such as Flash. So the motivation here again was that, as we know, cloud operations is human-driven, prone to knowledge gap. There's tons of observability data, large amount of incidents, and there are obviously tons, like several tools built by academicians and researchers and engineers. So, however, there's no standard interface or evaluation methodology which is followed today. So, I identified this opportunity to help researchers and developers to build standardized tools which can be better integrated and deployed and adopted at scale. In AIOpsLab, we have standardized an interface for plugging into the cloud infrastructure for evaluation, observability, reproducibility, and enabling these tools to scale for large amount of cloud systems and tasks and faults. Here you can see the architecture for AIOpsLab, where on the left side, we start with an agent which can interact with the orchestrator, which is sort of the abstraction which any agent can plug in. And this orchestrator is able to scale to various AIOps tasks such as detection, triaging, root cause diagnosis. It's able to interface with different workloads and different type of faults at different layers of the cloud stack. Here you can see a GPT-4 React-based agent, which is able to take multiple actions and leverage the feedback and signals from the cloud service, and then ultimately resolve real-world faults. The insights we had here was that observability is key. Unless we have the right signals being logged, the agent is not able to figure out like what to do. And secondly, we did observe that agents can take complex actions given continuous and accurate feedback. You can learn more about AIOpsLab here on this link, and we're happy to collaborate and have more and more adopters for this framework. With that, I'm going to thank all the audience for attending the talk, and please do reach out to me if you have any questions or if you want to collaborate or if you are interested in industry opportunities. And I also want to thank the plethora of collaborators I've had over the years, and some of them are listed here. Thank you.